In this video, we're going to compare reaction quotient QC with the actual equilibrium constant KC. So remember, with this QC, KC, or QP versus KP business, we ask ourselves the question. Is this reaction under these given conditions at equilibrium? If it's not at equilibrium, then which way will the reaction go to achieve equilibrium? Now, if QC is equal to KC, then you know that the concentrations or the pressures, if it's gases, the conditions are equilibrium conditions. And so those are the correct concentrations or pressures at equilibrium. But if your QC and KC are not equal to one another, which way the reaction will go based on the given conditions? Which way will the reaction shift to obtain equilibrium? So here I like to use the Gator rule. If QC is greater than KC, if QC is equal to KC, then you don't have to worry because you are at equilibrium. And then if QC is less than KC, okay, I can also put P here if you're talking about pressures and gases. So here we are at equilibrium. Here the alligator jaws are pointing to the left-hand side, so that's the reactant side. And here the alligator jaws in this third scenario is pointing to the right-hand side or to the product side. So the equilibrium will shift to the left, reactants. We're already at equilibrium here. And here the equilibrium will shift to the product side in order to obtain equilibrium. So which way will the reaction shift to obtain equilibrium given certain types of conditions? So here's our reaction. They give us the equilibrium constant at this temperature. And under these given conditions, are we at equilibrium? And if we are, then we're good. If not, which way will it go under these given conditions to settle and obtain equilibrium? So let's go ahead and do this problem here, comparing QC and KC, the reaction quotient with the actual equilibrium. All right, so these are the conditions that are given to us in this problem. C stands for concentration. We can also use pressure, but they give us a KC. And remember, this is always quoted at a specific temperature. So let's plug in these values into our equilibrium constant. Remember, it's products over reactants, each raised to its stoichiometric coefficient. All right, actually, this is going to be QC because we do not know if these are the actual equilibrium concentrations or not. And remember, QC and KC have the exact same formula, exact same equation. It's just a comparative tool. So NH3 here, by the way, this is the not symbol, which means initial. So we have 0.4048. You don't have to worry about units, so that's one bit of relief for us as we do these problems. H2, we're going to have to cube it, so it's 0.76 cubed. And products over reactants, N2, 0.60 raised to the power of 1. All right, so let's do this in our calculator and see what we get. So doing this, I'm getting 0.8, let's just say 0.87. And that's our QC, but our KC, if we're really at equilibrium, this whole quotient should equal to 1.2. Obviously, it's not 1.2, it's 0.87. So these are not the equilibrium concentrations. The question we have to ask ourselves is, where will it go to obtain this equilibrium? So this is where we will use the Gator rule. QC, put it first, and KC. KC is 1.2, and QC is 0.87. So we'll always put QC first for our Gator rule, and we know 1.2 is greater than this. The alligator jaws point to the right-hand side. They point to the product side. So we're not at equilibrium. The reaction is going to shift to the right, to the product side. So what will increase in concentration? Because the reaction shifts to the right, we will have an increased concentration of NH3 and a decreased concentration of nitrogen gas as well as hydrogen gas.